Hi everyone, my name is Jeff. I work at x.ai, where we build artificial intelligence, and I want to show you a little bit about how we stack that up. And so my cut at this talk is a little bit different than the previous two speakers in that the balance here is going to skew a little bit more to the human, a little bit less to the technical, but I'm going to try and connect the two. So I want to start with what we build, because that gives us a lot of context around what's the problem we're trying to solve. The problem that we encounter is all of us schedule our own meetings. We don't have personal assistants who decide when we can meet, look at our calendar, propose times, handle rescheduling, talk with other people about their availability. So we do all this ourselves. We think the best solution to this is to build a single-purpose artificial intelligence agent that is capable of doing this for you. We call her Amy Ingram. So let's show you what that looks like in action. Assuming this is connected to the internet. Let me try that again. There we go. Brief demo here. We'll give our marketing department. So, here we are. We want to have a meeting. So we make the request. We hand off the work to the artificial intelligence, Amy. Amy has the conversation with our guest. Our guest replies, says what they're available to do. Amy handles booking the meeting, and it just shows up on your calendar, taking on the task entirely for you. So, a couple obvious things there. One is that the user is communicating with the artificial intelligence in free-form natural language, in English text. Similarly, the artificial intelligence is speaking back in free-form natural language. There is no API to learn here. There are no special commands. This is a conversation with another person. It just happens to be an artificial person. So let's talk about the humans first, and then we'll talk about how they build what we just saw there. The humans that it takes on the tech team here are grouped into three key areas. The first is on that comprehension task. How do we teach an artificial intelligence how to comprehend written text? And the second is on the response task. How do we make an artificial intelligence speak? And the third is around the annotation, which is a component of the comprehension task. How do we actually get labeled data, which is a topic we just discussed a great deal. And then, of course, there's a bunch of folks on the business side doing things like selling our product and supporting our customers. That's not what you're here to hear about, though. You want to hear about the stack. So let's talk about the stack. Let's start with the programming languages specifically. Historically, we've really been known as a Scala shop, being highly principle-type functional programmers. Members of the team commit to the Scala compiler, give talks at Scala Days, Scala Exchange, etc. We really care about this as a sort of unifying principle, as a way that we structure our code. You can see a presentation from myself and my colleague at Spark Summit East this year on Spark as the gateway drug to typed functional programming. This is a core belief that we have about a way of structuring complex semantics within an artificial intelligence using sophisticated tools in a type system. But actually, if you go back to the very beginning of the company, we were entirely JavaScript. Our MVP was built using full-stack JavaScript technologies. And this was because we were starting with a problem that existed on the web. We needed to receive emails and send emails, and then we needed to build up the infrastructure to organize that annotation process. And then more recently, we finally expanded out that stack to include just one more language, and that language is Python, for pretty obvious reasons. And that's to be able to take on some of these sophisticated machine learning technologies that are being released primarily in Python, sometimes with native tooling underneath. So in terms of proportion, Scala is about 50% of our stack these days. The JavaScript is 40%, and the Python is 10%. But in terms of what we're looking to do in the future, we want the Scala to increase, and we expect that the Python will also increase, which means that we're going to be eating up that JavaScript functionality with other languages, basically because we want to increase the amount of machine learning code that is a core component from the Python, and then we want to structure the web services in a more principled manner than we are doing in the JavaScript. I see a lot of you seem to raise your hand when we ask questions about machine learning things, so I think a lot of you are actually quite interested in machine learning stuff. So let's talk about some of the machine learning side of things, the data science here. We started off with using traditional machine learning techniques, all the standard things that you'll find in any given library, just as a way of getting started, working with our unique data set and trying to see how tractable it would be to traditional machine learning techniques. From there, we deepened our capabilities to work with natural language comprehension by using specific NLP techniques like conditional random fields. There's a great talk on our use of CRFs from O'Reilly's AI conference last year by my colleague Angela Joe. If you have any interest in understanding how CRFs can be applied to a problem like this, I would encourage you to check out that talk. And then finally, as I mentioned before, we have introduced Python into our tech stack because we want to be able to use the latest and greatest coming out of the deep learning community. This is an extremely important capability, and we just feel like it would be a huge waste to not take this on and use it to power parts of the intelligence problem. So now I want to dive a little bit deeper than that sort of surface level into 4 techniques, approaches we take to how we have built up a company and a team to do these things. And the first of those is judicious determinism. So not everything that we have built is, in fact, a stochastic system. It's not all machine learning. This is not all statistically based. Here's an incredibly simplified version of our system architecture. This is the one that has a low enough detail that I can show it to you. And you'll notice here the components in blue are the parts that we think about as Amy's brain. They're not just about passing around emails through the internet, but rather they're about our core functionality. Within the big box around natural language processing, we're clearly within the machine learning domain. But within the smaller box around natural language generation, that is where we teach Amy to speak, that's purely deterministic. And so in that case, the core organizing principles are typed functional programming encoding business logic, which allows us to have a very designed user experience that results from a lot of human input. Showing you what that looks like in detail, here's an example of an email that is generated from that compositional system that speaks, given some general user experience and also some specifics about the situation. You can see that we know who are the people involved in the location that they're meeting. This is what that looks like behind the scenes. This is templating code in which we have the ability to inline variables about things that we know from other parts of the system so that we can inject that intelligence back into the conversational process. Next technique I want to talk about is problem decomposition. I showed you an extraordinarily simplified version of our architecture diagram for a reason, is that we think that a key component of how we're able to work on this problem in a tractable manner is to not merely treat it as a single monolithic task. Behind the scenes, Amy is using a very large number of models to solve a very large number of subproblems within the task of comprehending what is the content of an email about scheduling a meeting. Here's one view into why that's a little bit hard. This is a sort of toy example that allows us to speak about why this is difficult. This is a word cloud projection into 2 dimensions with color serving as a third from a neural network trained on a very early version of our entity recognition subsystem. When you look at the high-resolution version, which you can find on our blog, you'll see groupings of things like person names, like Amy and Andrew, the names of the artificial intelligences, as well as temporal expressions are grouped, I think, in the bluish stuff in the upper left. So that's statements like today, tomorrow, next week, things like that. Systems like this are pretty hard to reason about, and this is only one component of things. And so we strive to have very clear semantics around what subproblem we're solving, and then compose them together into an extremely sophisticated artificial intelligence that doesn't look like anything other than a person in its interaction. Here's another cut at why that is challenging, why that's hard, and why we have to think about this in terms of slicing up into multiple pieces. This is a Sankey diagram of a dialogue, and so this is some aggregate of conversations that Amy has had with our customers. So you can see in the big fat sections there that are a little bit shorter, you can see strong skills. These are things that Amy is able to comprehend well and act upon in an effective manner to get the conversational thread to terminate as soon as possible in the successful scheduling of a meeting. Which means that spaghetti that you see are areas in which at least the conversational path has taken a rarer turn, and as it gets longer and longer out towards my left there, you will see that those are longer dialogues which we would consider less successful in areas for future investment. So tools like this, which we build internally, allow us to target which components of the problem we want to work on next to have the greatest impact on our customer user experience. Third technique I want to talk about, and that is reactive systems. So for those of you who may be unfamiliar with reactive systems, This is an idea that was reproposed in something called the Reactive Manifesto a few years ago. The idea works like this, that we want to be responsive to our users. That is, we want to return from user input in consistent time-bound manner, which implicitly means that we need to be resilient to errors, and we need to be elastic, independent of the scale of the operation that we're trying to perform. Implicitly underneath that is that you're talking about a system that is probably not monolithic, that is not a single unit, but is in fact working in some distributed manner, passing messages back and forth. Reactive systems have been applied to a lot of different domains. I personally spent a lot of my time trying to apply reactive systems to the problem of machine learning. So you can see my book there on the left, which you can find on Manning, as well as I've given a large number of public talks on this topic, going through particular ways in which this interacts with how we interface between features and machine model learning process, the feature generation pipeline itself, how we collect data in this manner. This is a complicated problem because what we need to do here to feed all of those big neural nets that you saw is collect data at scale and learn on it at scale. Finally, the last technique that I want to introduce you to is a very people-centered technique. I call it data knots, although I think my CEO, Dennis, would probably call it Spartans. The idea here is this. Let's take a quick poll here. Who in the room would identify themselves as a data engineer? You like to hack on some Scala, you build Spark pipelines. Okay, so we've got a few. All right, now who in the room would identify themselves as a data scientist? You like to do machine learning research, iterate on, okay, so we have a mix of both. I think I might have seen some people raise their hands twice, I'm not sure. I hope at least someone did, because it's my view that these people are not different when put together in the right way. That they are not antagonistic roles, and that I'd actually like to use a completely different job title to refer to this class of work. And this is a core unifying principle to how we structure our work, in that we want data engineers, data scientists who are capable of understanding the problem of building an artificial intelligence and the problem of the software engineering necessary to do that at scale in a reactive manner. We want people who can do both of those things. We want them to meet in the middle and learn and grow from each other. So that's how we structure our team. In particular, that means that we do things like allow everyone on the team to choose their own work, to select the projects that we should build as a company, prioritize them, elect their own project leaders, organize technical practices around the things that they want to do, all fully autonomously and self-organizing, so that these people who take on a great deal of responsibility have the ability to contribute in that sort of multifaceted mode. And that's really the secret to success in something like this, that all of the things that I just showed you are not feasible without having a team as capable as this. This is just the tech and product team. I got tired from copy and pasting, and so this was about as many people I could fit on the slide. But all of these folks are functioning in this fashion. They think about the user experience of working with an artificial intelligence. They think about the challenges of collecting data at scale, of engineering features, of structuring business logic in a rational and logical and structured manner. And they're capable of doing all of this in a highly autonomous, loosely coordinated fashion to build up the user experience that we just talked about. So I made up a lot of assertions about this is a good way of working, this is a neat approach to the problem. Does it work? That's fair. Here's an example of one of the proof points we'd like to offer that this works. This happens all day, every day. You can see here that a guest on a meeting is inviting Amy to join a conference call because he thinks that Amy is a person, that Amy can speak on the phone. And so Amy has the capability to decline. And in fact, this happens so frequently throughout our system that this is an encoded system feature. We call this decline robot call. Amy has received gifts, gets asked out on dates at least once a month. We pass the Turing Test for a lot of people all day long. And this is a key judge of whether or not this is a useful and helpful user experience for people. The next step beyond that that I find really compelling to me is these are our customers who know for a fact that Amy's an artificial intelligence because they signed up for her on our website, and they still thank her in over 10% of meetings. This is someone who has taken artificial intelligence onto their team, treats them as a colleague. One of our customers even has a desk with a name tag for Amy in their office, so that when people come by asking, where is Amy, so I can thank her. And so we see a lot of people doing this, about 10% of all of our conversations. So that's my talk, fairly quick. that's my information. You can find me here on the internet, Twitter, x.ai, of course. You can come visit us down on John Street. And of course, like everyone else, we are hiring for people who want to be data nuts and build systems like this. Thank you all.